Hello guys! In this video we are going to see basic methods of integrals, and we are going to devote this video to inverse tangent integrals. Okay, probably it's not the one you like to see, but since it appears so many times, I think it's very important that you understand the process, how to integrate this type of integrals. We will need some notions of integration and calculus as usual, and we will need to simplify some mathematical expressions. Come on, let's see. An important one. Yeah, I know. It's scary at the beginning, but I hope you find at the end of this video you find it so easy. Let's see. The pattern you need to look for. When you are dealing with integrals, you are going to see a fraction. Look at this 1 plus a function squared. And on the numerator, I have the derivative of the function inside the square. Be careful, not including the square. Just the function inside parentheses, okay? As an example, we can use the function x only, okay? So if you take f as x only, you will have 1 plus x squared on the denominator, and the derivative of x is 1, it's on the numerator. So the formula tells you that this is the arctangent of the function between parentheses, the function that is squared, okay, but without the square, only the function inside. Okay, so this is very important. A lot of times you are going to integrate 1 over 1 plus x squared, so the answer is arctangent, the inverse function of the tangent. And also, you will see this pattern many times. We are going to deal with this integral in this video. Okay, look at this one. You can just see 2 over 1 plus 4 times x squared. The key point of these integrals is just to identify that you are dealing with an inverse tangent integral. Maybe you see this better if I write the integral like this. Look at this. I just write 2x, everything squared. Be careful because I cannot apply the formula directly in this quotient. I need to write it this way. So I got a function, the function is 2x squared. As you see here. And then the question is the derivative of 2x on top? Yes, it is. So perfect. The only thing that I need to do is apply in the formula and say that this is the arctangent of the function that is inside the parentheses, okay? Be careful. No 2x squared. It's a very common mistake to add here and square. It's not, okay? It's the function between parentheses. Another example, that one, 3x squared over 1 plus x to the 6th power. Okay. I see a quotient. 1 plus something to a power reminds me of this inverse tangent integral. So what happens if I write the expression like this? What if I don't write x to the 6th power, but I write x cubed squared? Remember that the original formula has function squared. So my idea is to put something squared at the end. So what happens if I write it this way? Okay, seems good. And also, the derivative of x cubed is on the numerator. Perfect. I got everything I need. 1 plus function squared and the derivative on top. Arctangent of x cubed. And I'm done. Okay? I'm not doing anything just by recognizing the pattern of these integrals. One more. Look at this. 10 over 10x divided by 1 plus 5x squared plus 1 squared. So, this one is easier to recognize. Why? Because 5x squared plus 1, it's a function, a square. Perfect. I got the shape I got before in the formula. 1 plus a function squared. The question is the derivative of 5x squared plus 1 in the numerator? The answer is yes, of course. 5x squared, the derivative is 10 times x. Oh, perfect. So I don't even need to rearrange anything or add any number. I got the derivative perfectly on the numerator. Perfect. So this is the arctangent of 5x squared plus 1, the function between parentheses. Don't put the square, okay, in here. Okay, this is just for the formula. Another example, piece of cake again, cosine of x divided by 1 plus sine squared of x. Okay, do you see the pattern? This is a fraction. On the denominator, I got 1 plus sine squared of x. So I got a function squared and the derivative is on the numerator. So let me write it again. So the derivative of sine is cosine. So this is the arctangent of sine of x. Okay, question. It's no, but think about this. Anytime you see a quotient, the first thing you need to ask yourself is this a logarithm? Is the derivative of this expression on the numerator? Be careful, because the derivative of sine square of x is not cosine of x. The derivative of sine square of x is, be careful, 2 times sine of x cosine of x. If you don't see that, write it apart and think twice, okay? Because this is not a logarithm. This is just an inverse tangent integral, in which I have 1 plus a function squared, and the derivative of the function sine of x is on the numerator. So, again, arctangent of sine of x. Another one, piece of cake again. But in this case, we are missing something. I see the function squared, perfect. I see the 1 plus, perfect. The formula seems to work perfectly in this case. The function is x cubed plus 10. What is the derivative of x cubed plus 10? Is 3x squared. Okay, I got the x squared on the numerator, but I don't have the 3. Can I solve it? Yes, because it's a number. So what I'm going to do, I'm going to add the 3 in here, and I'm going to multiply 1/3 outside just to compensate. Again, I cannot put a 3 because I won't. If I put a 3, if I multiply by 3, I need to divide by 3. So that is the reason I just put 1/3 outside. So now I have 1 plus a function squared, and on top we have the derivative. So this is the arctangent of x cubed plus 10. Multiply by 1/3 because I just needed this 1/3 to compensate the 3. So guys, what have we seen? We have reviewed the inverse tangent integral. It's very important that you review these ideas slowly. Okay, it's an integral that is going to appear many times, and recognizing is not so easy. So please review the video as many times as you need, and if you have any questions, ask us. Okay, thank you for your attention, guys.